Because logarithms are exponents, as we've said over and over, it shouldn't be surprising that the properties of logarithms are similar to the properties of exponents. And so we have three primary properties that we're going to use in many different contexts over the course of our work with logarithms. The first is the log of products. And so if we're taking the log, and it does not matter what the base is, log base 10, log base e, log base 2, whatever we want. But if we're taking the log of two numbers that are being multiplied together, so let's say it was the log of 2 times a, or the log of 5 times 4, then we could split that expression into two separate logarithms that are being added together. And the two separate logarithms are going to have the same base as the original, and then the two pieces, and if there were 3 pieces, we would have more logs to add onto our list, but the elements that are being multiplied inside of the logarithm get split up into separate logs that are being added together. And so this dovetails with our work with exponents. If we have 2 to the 3rd power times 2 to the 5th power, we know that we can combine those into a single expression. Same base, the base doesn't change, just as what we see here, and then what do? We add those exponents together to get 2 to the 8th. So the same idea here applies with logarithms. If I'm multiplying the two things I'm taking the log of, then I can split it into two separate logarithms that are being added together. Because again, a logarithm is an exponent. And then we see the same thing with logs of quotients. So if I am taking the quotient, if I'm dividing two things inside of a logarithm, then I can split that up, but now it's going to be two logs that are being subtracted. And whatever is in the numerator is going to be positive, and whatever is in the denominator is going to be in the log that's being subtracted. And so this is the same as what we experience if we had 2 to the 8th divided by 2 to the 4th. We know that we can rewrite that as a single base, same base, no change, just like what we see in this rule for the log of quotients, but we're just going to subtract these exponents. So 8 minus 4 is 4, so same thing here. Division within a logarithm translates into the subtraction of two separate logs. And then the last is our log of powers. And so if we think to our exponents, when we raise a power to a power, 2 to the 3rd raised to the 4th power, we remember that we're going to multiply those exponents. So we'd end up again with the same base, but now it's 2 to the 12th. We don't add the exponents in that circumstance, we multiply. So the log of powers is similar to that. If we're taking the log of something that has an exponent on the inside, so in this case log base b of y to some exponent p, what we can effectively do is we can take that exponent and bring it to the front and multiply our logarithm. So the exponent translates into multiplication. So we end up with this p times the log of base b of y. So these three properties allow us to combine multiple logarithms into a single logarithm if we're basically moving this way. We can take a single logarithm and expand it into multiple logarithms if we're moving that way. And then it also is helpful for circumstances where we have exponents or inside of a logarithm to bring those out should we need to, or more likely, if we have a coefficient out in front of a logarithm, we can move that to the inside of the logarithm as an exponent on what we're taking the log of. So in these examples that we see at the bottom, we have very complicated logarithmic expressions in terms of what's going on inside of the logarithm. So we want to expand this expression into a sum and difference of a whole series of logs using the various properties that we have up above. And so just like with exponents, there are often many routes that we can take that lead us to the same place. So the sequence that I'm going to follow here isn't necessarily the only sequence we could take to to expand this expression. So just keep that in mind. So for example, one thing we could do is we could go ahead and cube everything in this expression, but I'm not going to do that. I'm going to go ahead and use my log of powers instead, and I'm going to move this 3 to the front to get me started. So I have 3 times the log of x y cubed over z squared. So now I'm going to split up this logarithm that has a product and a quotient in it into three separate logarithms, one involving x, one involving y, and one involving z. Now I have to remember that I still have this 3 that's out in front of everything. So I'm going to include this over here, and then inside a set of parentheses is where I'm going to expand my expression. And so essentially anything that's in the numerator is going to be positive, and then I'm dividing by that z squared, so that's going to end up a negative logarithm. So I'm going to start off and I'm going to have log of just x plus log of y cubed, and then I'm dividing by that z squared, so it's going to be minus the log of z squared. So that's all inside of my parentheses after I've expanded that expression. I'm going to scroll down a little bit. So we have a couple more log of powers opportunities to apply. So this 3 here, I'm going to move to the front. So I'm going to make that 3 times the log of y. And I'm going to do the same thing here. I'm going to move that 2 to the front using my log of powers. So it's 2 times the log of z. And then the last thing I'm going to do is I'm going to go ahead and distribute the 3 that we have here to all 3 parts of my problem. And so my final expanded logarithmic expression with no exponents or roots inside of my logarithm is going to be 3 times the log of x plus 9 times the log of y minus 6 times the log of z. And if we go back to what I had said at the beginning that I did not do, I did not apply this cube exponent to everything inside of the parentheses like I could have. And if we take note, what would the exponents on that expression inside be? X to the third, y to the ninth, over z to the sixth, which corresponds to the same coefficients that we have in front of those logarithms there. So if we had done that first and then expanded the expression, we would have ended up in the same place as where we did going the opposite and bringing the 3 out to the front. In the next example, we're trying to do the same thing. Take this logarithm that has multiple elements inside of it and expand it into a series of logarithms. So we're going to start off and recognize that we've got two things that are being multiplied in the numerator. We have x times the square root of x plus 1, and then that is being divided by the e that's down on the bottom. So I'm going to have 3 separate logarithms. The 2 elements that are in the numerator are going to be positive, and then the division by e is going to give us a negative logarithm. So we're going to have natural log of x plus the natural log of the square root of x plus 1, and then that's going to be minus the natural log of what's in the denominator, which is e. So I still have a little bit of work that I can do here. Notice it says we don't want any roots inside of our expression. So this natural log of x, there's nothing more that I can do with it. But remember, root x plus 1, we could rewrite that as an exponent. That could be rewritten as x plus 1 to the 1/2 power. Rational exponents translate into roots. So then, if I see it that way, hopefully we recognize that we're going to be able to use that log of powers to move that 1/2 exponent to the front. So that's what I'm going to do here. I'm going to take this to the front, and so now I have a 1/2 in front here with the 1/2 gone there. And then for the last bit, natural log of e, we have some properties that we have studied before that are going to allow us to simplify that expression. Remember, natural log is really log base e. And so if I'm taking the log base e, the natural log of e, that's a circumstance where the base of my logarithm and the number I'm taking the log of match. And so in that circumstance, that always equals 1. So that means I've got a minus 1 as part of my expression. So our final result, natural log of x plus 1/2 times the natural log of x plus 1, and then this minus 1. Now one thing I'll point out, it may be tempting to think that we can expand this expression here, but to make it natural log of x plus the natural log of 1, but that is not correct. The log of products says we can only expand that expression if we have a product inside the parentheses rather than a sum. Logarithms don't distribute like it's a number or something like that. So this is the best that we can do on this expression. In our last two examples, we're just working in the opposite direction. So now we have multiple logarithms, and we want to rewrite this expression as a single logarithm. So in this first one, the first thing I'm going to do is I'm going to take these coefficients and I'm going to move them in so that they are exponents on the variables inside of the logarithm. That's my log of powers. So I'm going to end up with log base a of x squared minus the log base a of y cubed, and then plus, we still have that log base a of z. And so now I have this sum and difference of these various logs, and so I'm just going to move whatever pieces are negative. I'm going to rewrite this as a single logarithm, and whatever pieces are negative are going to end up in my denominator, and whichever pieces are positive are going to end up in my numerator. So to start off with, the first term here is positive log base a of x squared, so I'm going to have an x squared in the numerator. I have minus log base a of y cubed, so since it's being subtracted, that's going to go into my denominator. And then finally, I'm adding the log base a of z, and so that's going to go into my numerator. That's just times z. Again, remember, logs that are being added, we are multiplying. Logs that are being subtracted, we divide whatever's inside of those logarithms. So that's how we end up here. And for the last example, there's a couple ways that we can approach this. We could distribute the 1/3 to both parts of the expression and then combine the logarithms, or we could take the two pieces inside the parentheses, combine those into a single logarithm, and then apply that 1/3 as an exponent. So I'm going to go ahead and take care of the inside first. Again, it doesn't matter, we can go either way. So I'm going to have a 1/3 still out front, and then I'm going to combine these two logarithms inside the parentheses into a single log. And so since I'm adding those two logarithms, I'm going to take their insides and multiply them. So I have x times y squared. And now I'm going to take this 1/3 and I'm going to move it to the inside. So that's going to be the natural log of x times y squared, the whole thing, raised to the 1/3 power. And then probably it would look a little bit nicer if instead of having a fractional exponent, we rewrote it in root form. So we can remember that the 1/3 power is the cube root of whatever is that's being applied to. So I'm going to rewrite this as the natural log of the cube root of x times y squared. So we can just leave our answer like that.